Okay, so here we have a sample problem, and the sample problem says we have a 15-gram bullet, and it's fired from a fictitious gun, and the bullet leaves the 14-centimeter long barrel of the gun at 400 meters per second. Find the net force on the bullet. So if we write the things down like we did in Chapter 2, we could say that the mass, I see the mass right here, it's in the wrong units, but we do have mass. Mass is 15 grams. And we would have to convert that into standard units. So in 1,000 small grams, we have something called 1 kilogram. And if I multiply that across, the mass would come out to be 0.015 kilograms. So that's our mass. The initial velocity is going to be 0 meters per second, because when we're talking about this, we're saying that the gun has a barrel, and on one side of the barrel the bullet's not moving, and on the other side of the barrel the bullet is moving. So if you imagine something like this, there's one side and there's the other side like this. So if we say we're going to start over here, then we would have to say that we're ending here. And where we start, we would say the initial velocity is 0. And where we're ending, we would say the final velocity is 400. So when they gave me that distance, that's how I was able to determine the beginning and the ending point. So my beginning velocity is 0 meters per second, and my final velocity is going to be 400 meters per second. And then I have to look again. I see that this is the length of the barrel of the gun, and so that would be my delta x. But it's in the wrong units, because the standard units of length is going to be in meters. So I have to convert this and say in 100 small centimeters we have a meter. And so the centimeters will cancel out, so 14 times 1 divided by 100. So my delta x comes out to be 0.14 meters. Okay, and with those three things that I have here, I can go and I can find what I did in Chapter 2. I can find the acceleration. Okay, so that's what I'm planning to do right here, using these three givens to find the acceleration, because once I have the acceleration, the real question is, what is the net force? And what I'm eventually going to be doing is saying the net force, the sum of all these forces, equals m times a. So that's my ultimate goal. And I know what m is, I need to know what a is, and these are vectors. Okay. So if I, using these three givens and this unknown, the formula to use would be this one. So v final squared equals v initial squared plus 2a delta x, and when I plug that in, the final is 400 meters per second. We square it, equals, well, the initial 0, 2 is here, a is unknown, and delta x is 0.14. So this becomes a pretty big number. So the acceleration comes out to be 571,428.6. So that's half the problem right there. And once I have that, see, I really want to get the net force. So once I have the acceleration, I just plug it in, and I get the net force. So So when I do this multiplication here, I end up getting the net force, which comes out to be $8,571.4 newtons is the answer to that problem. Okay, so here we have another example. An example says we have a raft, and they give us the total mass. The total mass is 1,300 kilograms, and they say the raft is being paddled with a force of 17 newtons going to the east. They said the wind is also going to push on this raft, and the wind is going to push on the raft with a force of 15 newtons, which is going at an angle of 67 degrees northeast. And the question is, find the acceleration of the raft. Now, in Chapter 3, we learned about how to deal with forces and take forces apart. So if I looked at this picture as a top view, what I would have is I would have a raft, and they told us the mass, 1,300 kilograms, and they say that this raft is being pushed with a force of 17 newtons to the east. So I could go to the left or to the right. I'll just go this way. So that would represent 17 newtons going due east. And they also said that it's being pushed 15 newtons going to the northeast at 67 degrees. So instead of going straight up to the north or straight to the right and go east, I'm going to go 67 degrees. So it's going to go like this. There's another force of the wind going up like this. So this number right here is 15 newtons, and it's going at an angle of 67 degrees. So we have two forces acting on this object, and what we learned in Chapter 3 was never work with component pieces, never work with a vector going right in the middle. You want to use the component pieces. So I would say that this one's going to the right, and this one's also going up. So I would have to find F subscript 2, which is going in the y direction, so it would be the hypotenuse, 15 newtons times the sine of 67. And down here, I will say that this one will be F sub 2 in the x direction. This is F sub 2 in the y direction. So this will be 15 newtons times the cosine of 67 degrees. This number here comes out to be, well, let me make a table. So when I make a table, I'm basically going to take the forces and find the x and the y pieces. So I have two forces. So force subscript 1, it's only going in the x direction, so that's 17 newtons and 0. And force subscript 2 is doing a little of each. Force subscript 2, when I take 15 times the cosine of 67, it comes out to be 5.86. And if I take 15 times the sine of 67, it comes out to be 13.81. The way we did these in Chapter 3 was to go and sum them up. So if I add these two together, it comes out to be a positive 0.86, and this one here comes out to be a positive 13.81 newtons. So that's my overall force that the raft is experiencing right now. So if I were to erase this and draw a picture, the raft is feeling overall a force going to the right of 22.86 newtons, and the raft is feeling an overall force going up of 13.81 newtons. And this is a top view. Okay, we can't really show you this as a front view. So we're looking at a raft, we're looking down on it, and the person pushing the oars is going to the right 22.86 newtons, and the wind is making it go to in the north direction, 13.81. And how would we figure out the total overall force? Well, in Chapter 3, we learned something called drawing these things tip to tail. So if I draw them tip to tail, what I would do is I would start here, draw one first, and then draw the second one right at it. And so this thing right here is the resultant force. It's the net force. So how would I get the net force? Well, I'm looking at a triangle where the base is this number and the height is this number. So how would I find the hypotenuse of that? If I use the Pythagorean theorem and say a squared plus b squared equals c squared, then the c piece is always called the hypotenuse. And that would also be called the magnitude of the resultant vector. So I can get the this piece right here would also be called the magnitude. So the magnitude equals the square root of 22.86 newtons, square it, plus 13.81 newtons, square it. Take out your calculator and calculate. And so you square this, you square that, you add them together, and then you have to square root everything. So the magnitude will equal 26.71 newtons. That's my net force. So I found my net force now of 26.71, and I want to get the angle. At what angle is this raft going to be moving? Well, it's being pushed kind of a lot to the east and a little bit less going to the north, so it's going to be going this way. I'm looking for this angle in here. So you get the angle by saying the tangent minus 1 of the y piece, 13.8 newtons, divided by the x piece, 22.86 newtons, and that'll give me an answer of 31.1 degrees northeast. So that's my angle. And why do I need an angle? Because we're talking about vectors. And whenever you're talking about a vector, you need two things. The magnitude, which is a number, and you need the angle too. So every vector has two things. Okay. So I could erase this piece right here. And I could say, on this raft right here, there is a force which is going this way, and that's my net force, which has a number of 26.71 newtons, and it's at an angle, and the angle is right here, which is 31.1 degrees northeast. So if I know what the net force is acting on this mass, and remember the mass was 1,300 kilograms, as it's still, the picture is still over here, so how would I go and find the acceleration? And the acceleration formula is basically the sum of all these forces equals ma. This is a vector and this is a vector. So if I rearrange it, it comes out to be a equals the sum of all the forces over m. And in this particular case, A is going to be, we just found it, the net force. So it's 26.71 newtons divided by the mass, it's 1,300 kilograms. So A is going to come out to be 0.021. Now, acceleration is a vector, so it should have a direction. The acceleration will be in the exact same direction as the net force. So the acceleration should be pushing this thing in the same direction as the net force. So it'll accelerate at this same angle, 31.1 degrees northeast. So I could say here at 31.1 degrees northeast. And that's the complete answer for my problem dealing with the acceleration of a raft when they gave me two different forces acting on it at the same moment. Okay, so Isaac Newton had a third law when he was writing them in his book. It's called Newton's third law, and basically Newton's third law is summarized by the action-reaction law. And in words, basically what his law says is for every action on one body, there's going to be an equal and opposite action on the other body. I should say the other. And so what happened is, just to let you know, like, so I'm showing this truck pulling a little camper or something like that. So you see there's a little hitch down here. The hitch has a force which is pulling the hitch forward, but at the same time, the hitch is pulling back on the truck, and it's giving it a little bit of a resistive type of a force. And those are equal and opposite, and so they cancel out right here. If a kid gets mad and pushes the wall or punches the wall, as the kid's hand hits the wall, well, the wall will go and push back against the kid's hand. Okay? So, for instance, what stops the kid's hand from going forward and breaking the wall, say, well, the wall has to be strong enough to oppose that. So right where the kid is striking the wall, you'll have equal and opposite forces. You'll have something like this. Right where the kid strikes the wall, you'll have a force going this way, which was the force on the wall. But at the same time, the kid is pushing on the wall pushes back on the kid. So at the exact same time, there'll be an equal and opposite force, which will be a force on the child. Okay, so they're equal and opposite, and that's what Newton said. Every time there's an action, there's always going to be an equal and opposite reaction somewhere. So when you have a force, there'll be an equal and opposite force somewhere. The idea of this could also be like if somebody hits you, well, don't worry, you've already hit them back, say. So, for instance, when their fist hit you in the arm, simultaneously your arm was hitting their fist. So it was an equal and opposite reaction. One person hit your arm, and then your arm simultaneously hit the other person. Here I have a word problem, and it says there's a 900-kilogram car pulling a 700-kilogram trailer, and the car's engine has a 2,000 Newton force accelerating the car forward along the highway or whatever. Find the force in the hitch which connects the trailer to the car. So if I had to draw something like this, just roughly sketching it out, I will say I have a car over here, and I could draw this all with boxes, and I've got some type of a trailer here. Perfect. So the car is going down the road this way. So we're told this thing is 700 kilograms, and we were told that this thing is 900 kilograms, and they're moving forward. And we were told that the car has an engine, and the engine is causing it to accelerate at a rate of 2,000 newtons, but it's pulling a total mass of these two numbers here added up together, which would be 1,600 kilograms. So if we want to get the acceleration, we'll say the sum of all these forces equals ma. So the sum of the forces we were told is 2,000 newtons. The total mass, 900 plus 700, is 1,600 kilograms. And we want to find out what is this acceleration rate. So we take out our calculator, and we do 2,000 divided by 1,600. If I do that, I get the acceleration rate is equal to 1.25 meters per second squared. So that's the acceleration rate of the entire thing. So what I'm saying is both things are accelerating together as one down this road. So how could I find the force right here in the hitch? Well, I'm saying the entire thing is accelerating at 1.25 meters per second squared to the right. So if I, for a moment, I could delete the car. So if I delete the car, what I see is just the hitch. And I'm sorry, I see the trailer with this little line on it, and this hitch is pulling it forward with some amount of force. Well, I can find that force because that would be the only force which is making this thing propel forward. So how would I find the force? I'm actually looking for the net force on this particular mass. So the net force on that particular mass would equal the mass of the trailer times the acceleration. And we know what the mass of the trailer is. It's written right here. And we know what the acceleration is. It's written right here. So we can plug those two in. So if I plug those two in, I'll get the sum of all the forces on this trailer equals 700 kilograms times 1.25 meters per second squared. It's almost all in there. A little bit fell off. 875 newtons. So the sum of all the forces on that trailer equals 875 newtons. But that's what this is right here. That is, in fact, the force that's in this connecting piece. If it's a chain, we would call it a tension. If it's a rod, we could also call it the tension in the rod. But that's our force right there. So that is the force in the hitch. And if we wanted to check, and you don't have to check, but if you wanted to, what you could do is look at just the car. I've got the road, and I've got this car. And they say inside of the car, in the engine, we've got this force propelling us forward. So there's a force of the engine, which is 2,000 newtons. The mass of this car by itself is 900 kilograms. And we were told that we think the hitch is a force going like this, and we think the force there of the hitch is equal to 875 kilograms, newtons, 875 newtons. So what's the net force on this particular picture? Well, this is going to the right, so we'll add it. Plus, because we say sum, so let's add them all up. This is going to the left, so we'll subtract it. When we do that, what we end up with is 1125. So we'll say this is plus 1125 newtons. Okay. And what we're doing here is I'm looking for the net force on the car. And then what I could say is another way, the sum of all these forces equals ma. So the net force on the car is plus 1125 newtons. The mass of the car is 900 kilograms. And we want to know what is the acceleration of the car. Now, we already know this. I'm just using this as a check because we already know the car and the trailer should be pulling to the right, accelerating at 1.25 newtons. So I'm just checking. So if I calculate this, the acceleration rate does in fact equal, if you take out your calculator, 1125 divided by 900 does give me 1.2 meters per second squared. And that is exactly what we said. So we use this side as a check, and it works. Here we have a wonderful problem, and the problem says we have a child, and I forgot to write it, so I squished it in here. The mass of the child is 50 kilograms. That's about 100 pounds, so it's not a baby, okay? This is a 100-pound child, so I don't know what age we're talking about, but in the teens I would expect. A child of 50 kilograms is on ice and decides to push their parent, and I'm sure this is in a fun-loving manner. Their parent's mass is 80 kilograms. That's approximately 160 pounds. They're pushing their parents on ice so that the parent accelerates to the left at 2 meters per second squared. Two questions. A, find the magnitude of the child's push. How much force was used when the child pushed the parent? And B, find the child's acceleration by themselves. So if I had to draw this, I would say, here we are, and we have a parent, so I'll draw the parent bigger than the kid. I don't know why I've made the parent so chunky looking, but this is 80 kilogram parent, and the kid would be over here, a little bit lighter. Okay, and this is the 50 kilogram child. So what's happening is, with Newton's third law, the child is definitely pushing on the parent. So if the child pushes on the parent will slide backwards and to the left. So if the child pushes on the parent like this, then the parent will slide backwards. So if we look at the parent is now moving this way to the left. And we were told the acceleration rate is the number 2 meters per second squared. And that can only happen if there was a push. So we must have had a force on the parent. Well, we can calculate what that force is because we know if the parent is accelerating to the left, they have to have a net force on them. So the net force is going to be equal to ma, and we could say the net force is going to be 80 kilograms times a. In this case, a is a negative 2 meters per second squared. So this comes out to be a negative 160 newtons of force. So the child pushed on their parent in a fun-loving way with a force of negative, meaning going to the left, 160 newtons. Okay, so that's how much the child applied a push. But the question is also, find the child's acceleration while this is happening. You see, the child will not just push on the parent. simultaneously, the parent will be pushing on the child, even if the parent had their back turned. And I guess that wouldn't be so nice. But even if the parent had their back turned, if the child pushes on the parent's back, then the back of the parent will push on the child's hands and apply an equal and opposite force. So the child's pushing the parent to the left. At the same time, the parent will push this child to the right. It'll be the same type of a force. So if I could zoom in there to the child, okay, what you'll see is after this pushing effect, the child will also be sliding this way. So the child was pushed this way, so the force on the child is going to be a positive 160 newtons. It's going to be equal and opposite to what the child pushed on the parent. Over here, I had shown an arrow going to the left, and this is the force on the parent. And now I'm showing a force on the right of the child, and it's the same number, 160 newtons. Here we had a negative 160. The third law says for every action there's an equal and opposite. So these two numbers are definitely equal, 160 and 160, and they're also opposite. One of them's a positive and one of them's a negative. So if we want to know the child's acceleration, we would just say the sum of all these forces equals ma, and we're talking about the child, so it's a 160 newton force, and the mass of that child is 50 kilograms, and the acceleration is something we're looking for. So if we do the math out, the acceleration will come out to be a positive 160 divided by 50. You take out your calculator. It's going to be 3.2 meters per second squared. So the child, they have a mass that's more than their parent, more than half of their parent. So you see, the child has a smallish mass. It's a little bit more than half. So the child's going at a certain acceleration. The parent has a bigger mass, and you know they're moving at an acceleration rate which is smaller. Okay? The acceleration rate should be inversely proportional to the masses. So the big mass has the slower acceleration rate, and the smaller mass has the bigger acceleration rate, and they should have the same ratio basically.